Right.
You get the previous recording I sent you, by the way? I think I sent it to you on the slide. Recording. Oh, the link. Oh, yeah, they've all been uploaded. So it's, yeah, it's up. Something we do is like a drive. Yeah, people would yell at me on that stuff. So.
It is. Yeah. Alrighty. So we can just about get started now. Um, the kind of goal of today is to ease into the motivation behind attention, and then kind of how that relates to transformer models, which are very up and coming, kind of the state of the art thing. And we're going to be spending a couple classes going over like modern vision transformers, as well as like vision transformers as a whole. And attention is kind of a cornerstone of that is going to be very necessary. Um, to kind of give you an idea really quickly before we jump into it of what attention is, if I tell you to look for a certain thing in a book, like a certain chapter or a certain like phrase, what you can do is you can read the whole book, hope that you recall everything, and then kind of present that specific place as you read it. But a more informed way of doing this would be first to go to a chapter and then a certain like subheading and then find what you're looking for. That's kind of what attention is doing. It's focusing your efforts and your kind of your eyes on a certain location and blurring out the rest so that you can figure out what specifically to focus on during this like lookup process. And something that we're going to also be talking about is how this uses a query key value system to make more informed decisions, more informed guesses as to which things to pay attention to. The modern attention system is kind of focused on how humans read. So when we're reading a certain sentence, everything else is kind of a blur, and we're focusing specifically on the sequential words that we're looking at. Yeah, so attention allows models to focus on the important parts of an input and make an inference using a specific subset of data instead of taking in everything as a whole. Not all features are equally important, and that's something we're going to talk about more, is kind of figuring out a probability distribution to figure out which things are more likely to be more important than others. A big example of this is NLP and RNNs, so residual neural networks, are often used in NLP contexts. For example, sequence-to-sequence models are encoding sequences as a fixed vector, then decoding them to another sequence. An example of this problem is translating. So if I wanted to translate, for example, French to English, I start with a sequence, I'm encoding this, then decoding it into English. There are other kinds of models. There's like sequence to vector models, et cetera, et cetera. But sequence to sequence models have both pros and cons when approached from like kind of the lens of an RNN. And we're going to be discussing them through this lecture. There's a lot of content to discover. So this is going to go decently fast. Feel free to stop and ask any questions you may have. Yeah, so as you can see here on the left, we have a bunch of French words, and on the top we have English words. And you're kind of creating a map of correspondences where the diagonal maps certain French words to English words. And this is kind of the byproduct of attention. You're saying that like these words are more closely related to this based on their ordering, based on their structuring and position. And so I'm going to say that these input tokens have certain correspondences to output tokens. And the reason that the shading is different is because not all of these are one-to-one, but these are our best guesses as to which ones correspond to which outputs. So yeah, there are a couple of different types of attention. The two we're going to be kind of talking about are hard attention and soft attention. Hard attention predicts which indices are relevant at a certain time step. So you're kind of looking at all indices and trying to figure out which ones of these are specifically important. This is kind of hard to backprop through, and it requires a lot of computation because you're searching through the entire input representation for the most relevant input tokens. The other side of this is soft attention, where instead of figuring out specifically which inputs that we want to focus on, we create a set of soft weights with the softmax function to create a probability distribution based on the input tokens that indicate their importance. Then we do a weighted sum where we're constantly tuning these weights. And this gives us an expected value of which tokens are more important, which keys are more important. And we're going to be getting into that. And this intuition combines the representations of different features that we have. Soft attention is what is generally used, and it's something that we're going to be focusing on quite a bit. So yeah, we're translating from French to English. When translating destruction, we want to reference I can't pronounce that, but the attention weights will be tuned accordingly and corresponded to certain outputs. This is kind of the meat behind the motivation of soft attention, right? We have a database of features that we're interested in, and that is our French reference. And we want to convert these to an English sentence output to eventually make our prediction. So we have a certain sequence of French words. That's our first sequence. Our output sequence is going to be a sequence of English words. So the two kind of problems we have are relating French words to English words. That's one problem. And the second problem is making sure that this ordering makes sense. The order in which we get the French words is also the order in which we decode the English words. So there are two things that we need to do in order to make this distinction. We need one metric to determine importance. So what are we looking for in the input to correspond to the output? So this is how do I match a certain query to a set of given keys? These are going to be kind of represented as Q and K. And then we have a weighted sum of features corresponding to each importance weight. So how can I weight these different words, these different similarities to give an EV and expect like an expected value as to which words are more correlated? And this is getting the value from the key. If your prediction was really good, if you're really good, your key will be equal to your value. If you're not that good, you're going to be tuning these weights as you go through your this process to figure out which values are more representative than others. Yeah, so I think this is a pretty good illustration of how this system works in like a traditional encoder decoder system. So we have we've talked about like encoders and decoders previously. But if I am Iron Man and I want to translate this to Je suis Iron Man, this is translating in this case English to French. But we want to encode each word, and as I build an embedding and a kind of latent representation of these words, each phrase is picking up from the phrase before it. So this is a sequential model. Then we have a context vector, which relates H4, which is kind of a correspondence of the entire input, the entire sentence, and relates it to decoding sequentially as well. Then we go from S1 to S2, S3, S4, where H is our encoder creating these representations. We have a context vector that maps our full representation to our decoder, and then we slowly decode. And this takes those representations and puts them back into a form that we can consume. This is how a traditional encoder-decoder network works, where we have our inputs sequentially kind of processing, then we have a context vector that only takes in the last one. The difference in using soft attention is that now our context vector takes in information from each latent representation. We don't take this in just sequentially, but we're putting all of them into our context vector, then using them to decode, which means that given a certain S2, this only has the first two decoded right now. In order to come up with S3, we want to take S2, which is our previous kind of guess or our previous representation, and take it with respect to all of our different encodings, so these latent representations, which is why our two inputs are going to be an S vector and an H vector, where H is our encodings and S is our previous decoding. The next step is to create a score function to figure out what these similarities are between these. And this can be scored in like a variety of different ways. There's a general scoring where you have a weight attention matrix, which is tuned in the attention layer. You can just take the dot product of the S transpose and whatever your H embedding is for the encoder representation. You can concatenate them. You can take a softmax. There's a lot of different things that you could do. Notice how the softmax uses a weight matrix that's changed, but it doesn't actually use the encoding. It only uses the previous decoding method. And this is specifically by location. Then you're only taking into account the location of previously decoded representations. And kind of to give a summary of a bunch of other metrics that you can use. This is a whole bunch and the papers that correspond with these. But what these metrics allow us to do is, based on our encoding and our previously decoded considerations, can we come up with a relative importance? Can we come up with a scoring function of relatedness? What are we looking for based on what our current decoder state is? Which the only information we have at this point is previously decoded things. So yeah, again, S sub I is the decoder hidden state, and H sub I is the encoder hidden state. In this case, SI is the queries that we're looking for, and HI is the keys. For each SI, we want to find its relevance to each HI. And we're going to be kind of going over this. If you think of this as kind of like a Python dictionary, where you have a bunch of keys, and a bunch of like values that correspond to these keys. Right, we're introducing a query that we want to compare to each of these keys. So we're going to be doing this comparison, right? We're going to be taking like the dot product of these or put it through some scoring function. This will come up with a weighting, some kind of weighting. That we then want to apply to our values. And coming up with this can give us the relative importance of how our Q, which is kind of what we want to find out. Q in this case is going to be our SI, right? So our query is our decoded representation, and HI, which is our encoding, is going to be our keys that we compare against. The score is then passed through the softmax function to get the weights. So these weights will be generated through like a softmax function to get a like probabilistic representation of the relatedness of a query with a bunch of different keys. Yeah, so this is basically explaining that we take our feature, we calculate attention weights, and you weight all of our features using these weights, and then kind of come up with a linear weighted sum of all of our features. So yeah, the example before was global attention, where all input tokens are used to generate output tokens. This is computationally inefficient because we're doing this operation with each and every key that we have. But instead of summing and querying over all inputs, if you only query over a certain window of inputs. So going back to the book example, right? If we are trying to search for a certain thing in the book, do we need to look at how a certain word or a certain phrase corresponds to every other phrase in the book? Or for example, do we only want to see how it corresponds to the 5 pages before and the 5 pages after, which could save us a lot of computation. So kind of how with the convolution, you can go over, figure out which region is most important as your kernel slides. We want to have a certain window where we only query over certain inputs, and that's where like the notion of local attention comes into play. Heuristics can be used to figure out this window. So if I have a certain length input and a certain length output, ideally the ith output token probably corresponds to the ith input token. So for example, if I'm of course translating a series or of a sentence of length 5 from English to French, more or less this depends on the language and stuff, but the 5th token will be in the vicinity, the 5th output token will be in the vicinity of the 5th input token, and so on and so forth. So you can center a fixed size window around the decoder step. So like I was saying, 5 pages before, 5 pages after. And these can be used as heuristics so that when you're doing the learning process, you're creating a truncated Gaussian function to calculate these attention weights. And this Gaussian function represents kind of the distribution that your attention will follow. We're going to talk more about the linear layer and sigmoid function to like get these centers, but hopefully the kind of general motivation behind global attention and local attention kind of came through. All right, so attention for vision. This is something we're going to delve a lot more into next class and the class afterwards when we go over vision transformers and advanced architectures for vision transformers. But attention is simply a means to look up features. Like the example of looking up a certain phrase in a book, we're trying to look up features while being computationally efficient. And attention gives us that insight, that intuition. Something that we've talked about before are squeeze and excite networks when we talked about advanced architectures about 2 weeks ago now, 2.5 weeks maybe, where we can give attention channel-wise in an image and select which channel is more important. We can also give attention spatially, which part of the image is most important, and kind of redirect these features based on the importance. Yeah, this is kind of just explains that. We want channel-to-channel interaction. Squeeze and excite, this is kind of what I was talking about before. You globally pool to figure out your importance weights. You can weigh each channel individually. And then excite, you pass these weights through the MLP and rescale these feature maps to get a kind of weighted representation of which channels or which representations are more important than others. So instead of having to kind of take linear combinations of all of these channels, you now have a more informed approach of which features are more important to both save computation and make your final representation more accurate. Spatial attention is kind of similar to what we were talking about before, in that here we have a kind of text to sentence represent or image to sentence representation. We have an input image. We want to extract features using convolutions. Then we have a residual network with attention over the image, and we want to use the different attention weights that we've come up with to do word by word generation to create a sentence that describes this image. This is going to be a pretty high level explanation. We're going to get into more of this stuff probably in the future. But we want to extract a feature map of the image. And we've talked about this extensively, how we can use convolutions to extract key features. LSTMs, have we talked about LSTMs before? Really? Okay, yeah. So these are long short-term memory networks that allow us to kind of take little connections between certain words and keep those in mind as we kind of go over a long span of data. But yeah, essentially we're using an encoder LSTM and a decoder LSTM. We've talked about encoders and decoders at the beginning of this lecture. It's a very similar thing. We have weighted features that we then want to kind of correlate to words. So yeah, we also talked about soft attention, hard attention, and these also apply to spatial attention. So soft attention is differentiable. You can train with backprop, and because you're using like kind of a weighted probabilistic interpretation of this, it's very similar to the translation example that we went over, French to English. Hard attention is trained stochastically with sampling. So this is kind of a random sampling method that you have to use, given that you're trying to figure out the specific features that correspond an input to an output. So yeah, VITs, we're going to be discussing these in depth. So we're not going to spend too much time on that. And yeah, attention can be used in various architectures as well. We've talked about inception nets, how they work. Now, when you're doing this combination of features, you're paying close attention, no pun intended, to which features are weighted higher than others. So here you're kind of creating an intelligent way of selecting a kernel, combining these features, and again running softmax on the result to figure out which feature combinations of channels are more important. Okay, so this is also very interesting. So regular attention, colloquially, you'll take a combination of, for example, the words in the French language with the words in the English language to figure out what the translation is. But say you're doing a language modeling task where you want to predict the next word based on previous words. The most kind of representative structure that you have at that point are the previous words in the sentence, right? The previous words that you've already talked about, the previous words that you've already discovered. The idea is that words in a sentence have relationships between themselves. And that's where this notion of self-attention comes into play. And Viswanathan kind of talks about this in his Attention is All You Need paper. When you're decoding with an RNN, we want to use the additional information of other tokens that we've already kind of decoded previously in the sentence. You want to look up the tokens from the encoder, and that was kind of what we were doing prior to this. Self-attention is looking up tokens from the same input. So in this example, we have the red word is kind of, as we go through this sentence one by one, what we're processing. And the blue is what we're paying attention to. So notice there are different shades of blue. These are generated, again, using kind of like our score, our cross analysis to figure out which things we should weigh more than others. So if we have the FBI is, the words that are most important to predict chasing at that point are FBI and is, because these kind of give us relationships that we want to keep in mind. So instead of saying something like the FBI is run, we want to prioritize the FBI is chasing from our word bank or our universe of words, right? By the time we get to criminal, we want to get is chasing a criminal, right? So instead of choosing something like criminals or like criminality, we know that is and are used as kind of like singular words, so we could come up with the word criminal. That's kind of the motivation behind self-attention, is weighting the words before your predictive word to come up with a best guess for what your word could be. Alrighty, on to transformers. I guess we could take a quick breather here. See, are there any questions that you guys have, or anything you would like to add, Jake?
Yeah, specifically like what we're really gonna like care about from all of that is like self-attention, and then like soft attention. That's basically the building blocks that we're gonna use going from like here on board. So if people have questions on like the like p-value query thing, like looking stuff up, and the idea of like weighting them by different amounts based on how similar our query is to like any given key in our dictionary. Like feel free to ask, because that's really the main thing we're gonna use going forward. Just the other stuff is sort of like context, that this idea of attention and, you know, like keys and queries is used all over the place. Yeah, but self-attention and soft attention. In particular, if people have questions or need any clarifiers, any of those.
Yeah, just to reiterate, soft attention is one of the main focuses that we're going to do. It's what's used in the transformer model that's described in attention is all you need. The idea behind this again is that you're creating a probability distribution that you can pull from so that you can predict certain relationships. So you focus on certain features, you don't focus on other features. So when you apply your kind of product to your to a softmax distribution, this pushes things either closer to 1 or closer to 0. And we're going to talk about how transformer models as a whole can also solve problems with RNNs, specifically vanishing gradients, and when you have a lot of data that you're considering. Yeah, so kind of going into, oh yeah, sorry, go ahead.
As a quick clarification, for like for that model on the board, query would take in the K and then create the probability distribution to predict like our word.
So not quite. So you're taking the essentially dot product between your query and all of the keys. So for example, if I had a sentence like I like pie, then your query in your first step could be I, and your keys would be like and pi, and you would also consider I, right? And we're going to talk about this more, but when we take this in the context of transformers, you're actually going to be using matrices instead of like a one-to-one comparison. So then we would compare this similarity together. And then these numbers that we get, these are like our weights that are then going to be passed through like a softmax distribution. So in reality, you're comparing whatever you're currently on to the keys of a bunch of other things to figure out kind of like which lookup is most representative in this scenario.
Yeah, to be like really specific to like W1 is obtained by passing your query and your key through your similarity function. So like that could be like a dot product, which just your dot product is going to measure like how close those vectors are like lining up. So W1 is obtained specifically by just taking the similarity of Q and K1. Your second weight W2 obtained for Q and A2. And then all of our values, B1, B2, B3, B4, B5, whatever, we're just going to multiply them by the corresponding weight. So B1 is going to get multiplied by W1, B2 is going to get multiplied by W2. And then to get the value, the total value at the very end of that, we're just going to add all of our weighted values. We're going to sum together B1 times W1 plus B2 times W2, like that stuff. Does that make sense? Make it, hopefully makes it a little more concrete.
Yeah, that's a really good point. So this Q and K are being passed into the scoring function, of which there are many, as we saw before. And yeah, we also related these previously to H and S, which were our decoder and encoder in the like kind of, we started from the RNN, kind of showing how we have an encoded latent space and a decoded latent space, and how that corresponds to our Q and K. Yeah, so moving forward into complaints about RNNs, they are not very parallelizable, right? We want to take in each input as we go. We can't parallelize our operations, and they're very bad at capturing long sequences, right? If I had a very long representation of H's, I need to go through H1, H2, H3, H4 sequentially all the way to a however long my sequence is. And then I need to take this in respect to my like context function and then apply that to generate an output, right? So there's a lot of compute steps that are needed to calculate the relationship between a certain TI. And then if I add to that TI plus D, the amount of computations I do will scale linearly with D, and I can't parallelize any of these computations. So yeah, I would need to run the RNN D times, in that time, I might forget the representation come up with previously of TI. The solution to this is adding attention. So yeah, going back to kind of going into, sorry, the meat of today as well. Attention is all you need is a very cool paper that talks about getting rid of recurrence altogether and using self-attention to model sequences or groups of tokens. So going into the transformer architecture, we have similar inputs as before. We have a sequence of token embeddings and positional embeddings, which we're going to talk about. But essentially, to give a quick preface into this, again, if we have a sentence like "I like pie," the two things that I want to know are I want to embed these because our program ultimately cannot take in words, right? It needs to take in embeddings or numbers or vectors. So if I embed this in a certain, let's call it like E1, the embedding vector, this is one piece of information. But the second thing I want to know, especially if I'm doing something like predicting like the next word or like an intermediary word, right? I want to know the position of these because that matters a lot. So I also want P1, where these are positional embeddings. And by doing some combination of these, I get a representation that I can then pass in to my transformer model. And we're going to get into a little bit more about how to come up with both of these. But there are many ways to come up with positional embeddings. For example, like this is position 1, 2, 3 right now, right? This can be figured out using like sine and cosine functions to figure out where in a sentence you are, and keep that in mind as well. All right, moving into the actual kind of transformer model that's described in this paper. You have the big red cat, you have an attention block, and then a bunch of outputs that you want to come up with. Kind of going through this process, you have a multi-head attention block, then you have an addition and normalization layer where multi-head attention is essentially where you're running attention from a bunch of different points on everything. So instead of just having one representation where you have like scalar values that you're multiplying, now you're multiplying values across a span of H's or a span of embeddings or representations. And then you're combining these all together at the end, and you're doing layer norm on this, which we're going to talk about as well. Then we're running all of these through a feed-forward network. But the difference is now that I'm calculating multi-head attention for all of my queries against all of my keys, and these are matrices, now this feed-forward step can be done in parallel. And that parallelization is really what brings out kind of the merits of a transformer as opposed to other representations. So yeah, each token has a key query value, like we talked about. And for each token representation, we use its query to find the most relevant tokens in the sequence based on their respective keys. And this is kind of focusing in on what the multi-head attention block is. We want to calculate the importance with the dot product of the query and the key, and take that in a softmax representation to push values closer to 0 or closer to 1, and probabilistically then apply these to our values, and then take the sum of those based on their importance that we've previously determined based on the dot product, and that becomes the new representation of that token. And as we go through this attention process, we're refining our weights, thereby refining how we weight our values, thereby refining our final prediction as to which words can come next. This combines residual connections and layer norms to come up with a representation that kind of alleviates vanishing gradients and provides a representation that is accurate. We did talk about vanishing gradients before. If you have gradients that are like slightly smaller than 1, you can, as you multiply these over the course of a long or a very deep network, these are going to be pushed towards 0, and your value is going to be like infinitesimally small, very, very small. But yeah, at the end of this, we have a linear layer, and this is kind of essentially what we're doing. You have an H depth of Qs, you have an H depth of keys as well, and you're calculating this because you have WQ, WK, and WV. So this is essentially like a linear matrix multiplication that we're doing. So yeah, you're applying a linear layer to get KQV from the input embeddings. You have your E, which is like your embeddings for each of these words. You have WK, WQ, and WV, which represent the different weightings of different values of keys, different values of Qs, and different values of Vs. And we're doing mass matrix multiplication, which is very easily parallelizable on CPUs. So that also saves a lot of computation. You're applying a linear embedding to get your final KQV from input embeddings. And like we talked about before, what we want to do is find the dot product between the queries and values. Each token directly attends to every other token. And the connections between arbitrarily long inputs is O of 1, because we're doing this dot product of each Q with each K. And because this is a kind of a matrix that we're multiplying, no matter how big our input is, we're still doing this one operation. So yeah, after this K and Q multiplication happens, for a single KQ multiplication, we apply a softmax distribution based on the dot product values that we get. As you can see, some of them are higher, they're pushed towards 1, others are lower, they're getting pushed towards 0. And then we reweight our V's based off of these W's that have been pushed into a softmax distribution. Once we multiply our weights by our values, we essentially have a weighted sum of V's, and by adding all the V's together, we come up with a final value. And this is on a token by token basis. Scaled attention is where we scale our dot products with 1 over square root of D. And this helps because dot product values will grow very large with high dimensions, right? The kind of dimensions of your matrix are going to be extremely big. So your value is going to grow because of that as well. Some components of softmax can have extremely small gradients because of this, because as your values grow really big, if something is like an order of magnitude less than something else, those are going to be pushed towards 0 extremely fast. So by dividing by 1 over square root of dk, which is your, I guess you could consider it your distance or your size, you're scaling the dot product based on its number of features or its depth. This is to standardize things and ensure that you don't have some gradients or some components that are automatically being pushed to 0 just because you're multiplying more things. So your number is obviously going to be bigger. Yeah, so like I was talking about before, in multi-head attention, we're projecting each key, Q, and V that corresponds to a token H times. So essentially you have an H depth that is then reconcatenated after your tension operations, then multiplied by another weight matrix. This models different representations of the same tokens as well as its different functions, right? Because you have now an H depth you can consider to the matrix multiplication that you're doing, you're able to consider a lot of different representations of your data. And dropout is used after the multi-head attention block. We've talked, I don't know if we've specifically covered dropout before, but this is a way to kind of alleviate overfitting and make sure that we are actually learning an accurate representation of data. So yeah, I really love this diagram. It shows that you have a WV, WK, and WQ that correspond to whatever your Q, K, and V are. You're using a scaled dot product to get an initial like attention estimate. You're concatenating all of these layers together. You have H layers, right? You can see that for each of these, the depth is H. You have like H channels or H representations that you're kind of using to get intuition. You're concatenating these together, passing it through a linear layer, right? But this feed-forward neural network can only take in one vector. It can't take in a matrix of values, which is what you come up with, because you have a matrix of values, a matrix of keys, and a matrix of queries. Your result after you concatenate is going to be a matrix of these vectors. We then want to apply a transformation WZ onto these vectors to get a specific vector that we can pass into our feed-forward neural network. And this is kind of what we were talking about before. This Z, this resultant, is calculated by the softmax of taking your Q times your K, dividing by the dimension of one of QKV. They'll be the same dimension ideally. And this represents the size of Q and K. So that if you're doing this QK multiplication of matrices of drastically different sizes, you're kind of normalizing now by the dimension that you're multiplying by. And then pushing that towards a softmax. Again, this gets your scaled weights, and then multiplying that by your value, which is exactly what this formula describes. This will get you a matrix, and then you're passing that through another weighted matrix to get a singular vector that gets passed into your feed-forward network. So yeah, something else you can notice is that you're adding residual connections, as you can see. We talked about this in advanced architectures as well when we talked about residual neural networks, but this is to remedy vanishing gradients in models with a lot of layers, very deep networks. The next thing to talk about is layer normalization. These two both contribute to the add and norm step, respectively. Batch norm, we talked about before, is kind of normalizing a certain, like, you could think of it as horizontal batches, making sure that the mean and standard deviation are normalized. But here, statistics are calculated for each sample with respect to the parameters in each layer. So you can think of batch norm as kind of like a horizontal norm, and layer norm is actually like a feature norm that is done vertically. I believe there is also a slide detailing this specifically, but hopefully this add and norm step makes sense now. You're adding a residual and you're normalizing by feature. So yeah, batch norm is where for all training samples, you are kind of normalizing your data horizontally. Layer norm is in a certain batch, I want to normalize each feature dimension. And that is what's used specifically in attention. All right. We can now move on to the feed forward kind of. Actually, let me pause here for a quick second. Are there any questions? This is quite a bit of content. Kind of been just charging through it. And Jake, if there's anything else you want to add.
No, I think you're doing it though. But just do people have like questions on any of like the previous stuff too? On like there was a nice diagram with all of the different like attention weights and everything. Like that stuff too. So that might have been a on
This one?
Yeah, so like on these graphics, like get out like this stuff right here. Like, do you have questions on like any of this stuff as well here?
I think one of the easiest ways or the most intuitive ways to think about it is that you have a query, which is like kind of changes depending on which token you're on. You're trying to find like in like your universe of information, what is most related to it. So it's like you're trying to look up something, but you don't know exactly what you're trying to look up, right? We talked about before. So by multiplying this Q and K or passing it into some scoring function, in this case, it's the dot product as described in this attention is all you need paper. We come up with some kind of dot product. We're passing that through a softmax function, and that is pushing values depending on other values, right? Obviously, certain scores of these QK comparisons are more important than other scores. Then you're just multiplying that by your value. That determines which values are most important, and you're just taking a weighted sum. So this will implicitly consider kind of certain similarities and differences.
So is the whole process just to like calculate W and multiply by VI, sum that, and now we get WZ. Then we get the final value and then feed that into the network.
Yes, so you have more or less that is what we're doing here. Once you have the weighted sum of V, in the big attention, in the multi-head attention model, since we have a matrix of these values, this produces multiple vectors, right? Then we can only pass one representation into our feed-forward neural network. So we introduce a new matrix that's tuned or like part of the training process to just do a matrix multiplication and get a singular value, basically. But yeah. Up until here, yeah, that's exactly like you described. Alrighty, so the feed-forward neural network is two-layer neural network where you have weights shared with regards to position applied individually to each token embedding, right? So this kind of represents the combination stage that we talked about before, where you have after this a residual layer, residual connection, and a layer norm applied. And dropout is used after the feed-forward block to ensure that you're not overfitting to a certain representation. Yeah, so you sum reweighted Ks, put that through a residual and layer norm, combined with the input embedding, right? This is where your residual comes from, whatever your initial embedding is. And then, yeah, you pass each of these now. Now you have a value, right? These are the representations after your multi-head attention and residual nip layer norm. So this is after the meat of the transformer, right? We've already done all of our operations. The next thing that we want to do is we want a position-wise feed forward or a one-by-one convolution. This kind of depends on what application you're doing this for. Is this like a VIT? Is this like kind of like a predictive model for sentences, right? But we want to pass this through a multi-layer perceptron to give us our final value and a representation that we can comprehend and understand. And we do this for each and every value. And this is, again, these values have already been generated. These are your weighted sums that have now gone through a layer norm and a residual. And the beauty of this is that notice like we are doing an MLP for each of these different things. But again, this can be parallelized, which is really awesome because previously in residual neural networks, a big problem was being able to not parallelize anything. But now each of these MLP steps can be parallelized. You put these through one more residual and layer norm to get an attention block output. So again, you're now translating these new values into embeddings, and you're able to combine again using residuals, passing it through another layer norm layer. So all of this is just kind of getting more in depth into the actual like implementation described in this paper. But essentially it's just a combination of like residuals and layer norms that you're putting your data into. So yeah, this kind of like ends the transformer architecture that's described in Viswanathan's paper. Now this I kind of introduced this before, but position embeddings. Because the architecture is not inherently sequential, if we just pass in embeddings, you're kind of doing this QKV process of calculating like a representation very uninformed because you don't have any position information. You can change this by changing the embeddings that you're passing in to include position, where instead of everything attending to everything else, you're focusing on a certain window based on position information. There are a couple solutions to this, sinusoidal embeddings. So you have a fixed equation that you generate a P1 vector off of, depending on like other combinations of features that you have. And this is like a very simple formula. Or you can have learned embeddings, which is where you're learning the position of certain words in a sentence and using those to make informed decisions. Yeah, so another thing that is kind of introduced is having a dummy token, which is attached to the beginning of input. This is often used for if you are trying to predict like the next token or the next word in a sentence. If you're trying to take in a sentence like, I loved this movie, right? Say I want to do sentiment analysis on this sentence, which is like a very common NLP task. There are a lot of like databases. There's like an IMDb movie sentiment database that's really commonly used. Say I want to, instead of a sequence to sequence model now, I want to do sequence to vector, right? So sequence to sequence, an example of that, like we talked about, would be translating French to English. A sequence to vector model is now, I want to take this sentence, I love this movie, and I want to give it a score where the first value of our vector is bad, the second is good, right? So this I'm gonna have like I do this math correct. I think it's 8-8. Oops. Yeah. So you have a good score and a bad score. That would be an example of sequence to vector, and this could use CLS tokens, where we want to use the output representation of the token for downstream tasks. So yeah, the math here we really talked about before. You have a Q input, K input, V input, and we're multiplying our Q times K transpose, doing this dot product, and this is essentially a big matrix multiplication, where we're multiplying our Qs and our Ks to generate Ws, and each I represents our weight. And this representation in particular is our weight before we pass into our softmax function. So we represent each I as a QK product. We pass these into our softmax. We get a weights matrix. We multiply those with our values. Again, this is a big matrix multiplication. We get our weighted sum. And that is our attention. This is exactly what we calculated before. And this is exactly what's described in the paper. Notice how attention is really just large matrix multiplication between your query key and ultimately your value. Again, your distance term at the bottom kind of scales based on the size of this multiplication that you're doing. And yeah, there's a ton of operations because you do have to multiply these matrices, but these are huge matrix multiples, which is super parallelizable on GPUs. So this is very computationally efficient and scales very well on a kind of like distributed system, even though there are a lot of operations, which is why this kind of brings us to a better conclusion than what we previously had with RNNs, right? We can parallelize this no matter how big our input is. And yeah, that's basically the meat of it. There's a lot of other things that we're going to be talking about in this class. Sequence models, there are encoder models for BERT to generate your embeddings. BERT is awesome. It's used in a bunch of different NLP tasks. It's a transformer model as well. Decoder models they're a little more complex. Have we talked about GPT already?
We're actually going to talk about this. So
Oh, okay.
I wouldn't stress this, just the basic like transformer architecture in the city of like every single token is like comparing itself to every other token that we have in our sequence. That's really like the meat of it. Yeah, all this other stuff it's not going to be necessary for us. It's more for context. All of things.
Yeah, a lot of different developments in this field. And yeah, I think that's pretty much it. Revisiting the problems with residual neural networks. We had long sequences, but now because you're attending to everything, we have constant operations. Even if we're adding an arbitrary distance between our last embedding and like the new stuff that we want to consider. Before we had a sequential model that wasn't parallelizable. Now we have matrix operations, which are super parallelizable. So we kind of solved the problems that we had. This isn't even inherently sequential, right? We have these position embeddings, which contain some position information, but we don't have this inductive bias where we're giving it a semblance before that. I first need to process this, then this, then this, then this, right? So you're introducing before some inherent bias in the assumptions that you're making from the data, which is that this comes before this comes before this. So unlike RNNs and CNNs, which will impose translational invariance or inductive biases, we're not doing that in transformer models. And that's pretty much everything. Yeah. Thank you guys for coming. We're right on time. If you guys have any questions, feel free to stick around.
Yeah.
But
Yeah, perhaps